All right, so in this video, we're going to take a look at some examples where we search for the absolute maximum and absolute minimum values on these closed intervals. And so in the last video, I told you that we're going to look in two places. We're going to look at the endpoints, and we're also going to look at the critical values. So the endpoints are given, so we can just kind of sit on those for a minute. The critical values, though, remember, they'll be found by taking that first derivative, which in this case is 8 minus 2x, setting it equal to 0. Again, we take our first derivative and set it equal to 0 because we're searching for the places where our tangent line will be horizontal. Our tangent line will have a slope of 0. So when we solve this now, we get x equals 4. So this guy here, this is our critical value. It's not our answer yet, but it's a part that we need to take into consideration that could possibly be an answer. So now, to test these, we're just going to really think very basic. I need to test the endpoints at 0 and 6, and then a critical value at 4. So I've set this up in such a way that it's going to remind you to find f of x, we're going to take 0 and we're going to plug it into f. We're not plugging it into the derivative, we're plugging it into f. We're comparing these y coordinates on the actual function. So when I take a 0 and I plug it in here, I get a 0. When I take a 4 and I plug it into the original function, I get a 16. And when I take a 6, once again, into the original function, I get a 12. So all of these are y values. The overall lowest y value would be this guy right here. So this would be our absolute minimum. The absolute biggest y value would be right here, so this would be our absolute maximum. We're guaranteed at least one of each because we're on a closed interval. I would encourage you to go to Desmos, graph this parabola on this interval, and you would find out that your absolute lowest point on the graph is here, and your absolute highest point on the graph is here. Okay, for our next example, we've got a new function and a new interval on the interval -1 to 4. So the same basic idea. We're going to test critical values, and we're also going to test the endpoints, -1 and 4. So let's come over here to these, or to the first derivative to look for these critical values. So when we take this derivative, we get 10/3 x to the -1/3 minus 5/3 x to the 2/3. Now I've said it was coming all along. We're going to take this, we're going to set it equal to 0. So we should probably be prepared to simplify this. When you simplify this, which is very similar actually to a couple of the problems on that chapter 3 algebra trig review that you would have done, this ends up being 5 times 2 minus x all over 3 x to the 1/3. When I take this and set it equal to 0, you can see how easy this would be to solve. So the first thing that I would do is in solving this, I need to understand a few things. When I want to actually solve this set equal to 0, you can take your denominator, multiply it off, and then you're just solving this numerator set equal to 0. And you can see when you do that, you get x equals 2 as one of your critical values. Now I say one of your critical values because let's think about what's happening here. It's kind of hard to see if you're not really on the look for it. When I come up here to my original function, my domain of f is going to be -infinity to +infinity. I know that because this quantity right here is squared, which is always going to make things positive, and in fact this is a cube root, so it wouldn't matter anyway. Same thing here, this is a cube root, so it wouldn't matter if it's positive or negative. You can take the cube root of anything. So the domain is -infinity to +infinity. But when I come down here now and I look at my simplified first derivative, another reason why simplifying is really important, I see that x cannot equal 0. So I see that the domain of my derivative is -infinity to 0, union 0 to +infinity. And if you guys remember what that is from early in chapter 3, that is a non-differentiable point. All right, x equals 0 is a critical value. So our critical values are still 2 and 0. X equals 0, though, is a non-differentiable point. It is a point on your graph, but it is a point where the derivative does not exist. So please be on the lookout for those things. I'm going to remind you real quick of a page 110. They have a bunch of different pictures of these non-differentiable point scenarios, things like cusps and corners and vertical tangent lines. And some of these, if you look carefully, can be maxes and mins. So we absolutely have to include them in our critical values and our list of things to test. Okay? So again, be on the lookout. Yes, we need to test those endpoints, and we also need to test the critical values. But as a part of those critical values, we always need to include non-differentiable points. Okay? So let me come over here now and set up my table. I'm going to have x and f of x. I'm going to need to test -1, 0, 2, and 4. So I've got my -1, 0, 2, and 4 that are needing to be tested. When I plug those numbers now back into f, into this guy right here, I'm going to get a 6, a 0. Both of those can be done pretty easily without a calculator, but the other two, a calculator will certainly be helpful. This one gives us an approximately 4.76 value, and this one is approximately 2.52. Okay, so if we're looking now for our highest and lowest points, we're looking for the biggest and smallest values of y. So this guy here looks like this would be our absolute max, and this guy here would be our absolute min. So had we not saw that x equals 0 was a critical value, we would have missed out on that absolute min. So be sure, take a minute before ending this video, go into Desmos, graph this on this interval to not only confirm our maxes and mins, but to see what kind of non-differentiable point we're dealing with here at x equals 0. Okay, the last thing that I want to say, two last things I want to say before ending the video. When you have your critical values, something that some textbooks throw at you, others don't so much. Let's suppose we had gotten x equals 6 as a critical value. We would not need to test that in this problem because they only care about -1 to 4. So just make sure the critical values you're testing are within the closed interval that you've been given. Okay? The other thing, the final thing that I want to say is that remember the theorem says you're guaranteed at least one absolute max and absolute min. Had we gotten something like, let's say we had a number like 3 here and we got a 0 here. Well, this also would have been an absolute min. So we would have gotten 2 absolute mins. So multiple absolute maxes and mins are possible. Of course, they would be the same thing, but be on the lookout for those as well. So beyond that, hopefully these concepts are pretty intuitive. This last example was a little bit tricky because of what we had to look out for with that x equaling 0 being a non-differentiable point. But hopefully it all goes well, and we're moving on to the next.